mess with data here. It's what it is. These are the...
All right, we're going to get started. So it's my pleasure today to introduce Professor Matthew Turk, who's here visiting us from the University of Illinois. So Matt got his PhD in physics from Stanford in 2009, working with Tom Abell on the formation of primordial protostars. From 2009 to 2010, he was a postdoc down the road in San Diego. And then from 2011 to 2013 was an NSF fellow at Columbia. In 2014, as I mentioned, he moved to Illinois, where he is an assistant professor at the University of Illinois and also a research scientist at the National Center for Supercomputing Applications. And today he's going to tell us about promoting inquiry with software. So thanks for joining us.
Thank you. So thank you very much for giving me this opportunity to come here and talk with so many of you. As Gwen mentioned, I'm a research scientist at NCSA, which is a place that's done a lot of computing work and software development. I'm a research professor in astronomy there, and so one of the nice things about NCSA in particular is that it has a lot of astronomical ties. It was founded to, among other things, to study black hole collisions numerically, and it's been the site of many different developments of codes. Even the ENSO code, which I did my thesis work with and which I've worked with, was actually originally written at NCSA by Greg Bryan when he was a grad student there. And so I'm really happy to come and talk with Carnegie folks. It's really impressive to me how much history and amazing scientific work has happened here. Yesterday, Cindy took me on a tour of the vault, and it was super cool. I want to say thank you again. I guess it's a tradition that all the colloquium speakers get to shatter a plate that Hubble observed with. So thank you very much for having me here. And thus ends the jokes. So the thing that I want, the metaphor that I've built this talk around is that of scale. And like many of the different words in the English language, scale has different meanings when you talk to different people. And I'm going to talk about a couple different meanings of scale, particularly eventually as it relates to software. But first I want to start by talking about scale as it relates to what people think about when they think about supercomputer simulations, right? Scale is where you've got a whole bunch of really big numbers, and then out of that, those big numbers get crunched down and they turn into science. And I guess one of one thing that I've been involved with in the past has been something called the dark sky simulations, where I talked a little bit about this at tea today. We evolved 1 trillion particles over cosmic time. It was a big volume, and then ultimately, you compress this down, get a mass power spectrum. So I'm going to put up the name of the collaborators here. But when we talk about scale, the thing that we stumbled upon as we were running these calculations was that the scaling of the simulation was very different from the scaling of the scientific output of that simulation. This is a plot that was made by Sam Skillman, who's listed on this list, who was one of the people that was deeply involved with running this calculation. And what you can see here, this is each point on this is a particle count at that particular time, right? So you can see there's this linear relationship. As time goes on, well, I guess it's a log relationship, but there's this relationship here where you can see as time goes on, the number of particles in the fiducial simulations goes up and up and up and up, right? We've got more and more particles, more and more impressive calculations that are being done. And what Sam did that I thought was really cool about this was that he added a circle indicating the citation count for all the papers that were published with these calculations where the citation count was greater than 100. And there are a couple outliers here, like this one right here. Does anyone recognize what they think this one might be? It's right at 2005. A lot of citations. Yeah, Millennium. So the Millennium simulation was extremely successful. There have been a couple other simulations like here in the mid-1980s. I think this was one of the TREE PM papers or something. But for the most part, you can see that particularly over here, post-2010, the number of citations of these so-called hero calculations, these calculations that take days on the most powerful supercomputers in the world, is actually not that high. So if we think about this in a different way, we can evaluate the cost of something like this. If we use the 4-byte float, so that's a 32-bit float, as our fundamental unit, we can actually evaluate the cost of doing a calculation. So if you look at this, and this is as of 2014, so almost all of these numbers, except the ones I'm trying to cover up, have gone down in that time, possibly by orders of magnitude. And this data is courtesy Mike Warren, the leader of the team that I just described. A peak flop on a GPU costs about 8 times 10 to the minus $18. That's really small, right? That's immeasurably small. Reading something via FedEx, so if you pack up a hard drive, you send it, you get it. You can get that for about 4 times 10 to the minus 12. If you do an Amazon Elastic Block Store, it's about 1.4 times 10 to the minus 8 per float. A photograph is about 4 times 10 to the minus 5 per 4-byte float. But human labor for 1 second costs 2 times 10 to the minus $3 to do a single floating point calculation. Now, if you compare that to, human labor for 1 second, regardless of what you're doing, costs about 2 times 10 to the minus $3. And so people are by far the most expensive. If you look at the cost of writing a single line of software, it's about $10. This comes from, there are evidence-based studies that look at the productivity of software developers, and this number will only go up when you're looking at domain specialists like astronomers, astrophysicists, people that haven't necessarily been trained in software engineering. It costs about $10 to write 1 line of software. That's a lot, right? Especially if we're comparing that to the cost of a peak flop on a GPU.
How much to debug it?
Right, we're including. I'm including that. Yeah. So this is like this is averaged over a large boxcar.
I want everybody to know I'll do it for $5.
Oh, great! Now people are undercutting this. I was assuming there was going to be another bid.
That was going to
Sold.
Yeah. So I'm going to step away from this metaphor for a moment, or from this aspect of scale for a moment, and talk about scale and what scale means to me. So as Gwen mentioned, I did my work on the formation of the first stars in the universe. And so to me, scale often, naturally I think about this in terms of the length scale. We have to simulate 10 to the 6 solar mass halos, but they need to be embedded in some box so that we get the right wave numbers in our cosmological realization. But we've got turbulent mechanisms that function all the way down to sub-Earth radius. So this is an image of one of the simulations I ran, not for my thesis, but similar to the ones I ran for my thesis. And these length scales are proper, non-co-moving.
I think we need to take the lens off the screen.
Oh, I'm sorry.
It's not you.
Okay. Well, if I'd used a better color map, maybe it would be better. This one in particular is I love this color map because it speaks to me, but it's also really bad for people with reduced color sensitivity. So I apologize. Some of the images in this are not good for reduced color sensitivity. Every time I click, we're going to go in by a factor of 4, centered on this. So you can see as we go in, we're starting to see different structures come out. And actually, one of the things I want to highlight here is that the color bar is also going to change because it's basically impossible to represent all of the different length scale or all of the different density scales simultaneously. And I want to highlight here. You can see that there are some low resolution regions here. That's going to be something that I mentioned later. As we zoom in, now we're down into the parsecs, you can start to see different structures evolving. And through this whole process, different chemical processes are occurring. We're doing many different things. But we can keep going in. And so we have all these different scales. And now we're here at, and don't forget the 1e to the 4 here, but we're now at tens of thousands of AU. We can keep zooming in factors of 4 each time to the point where we're actually at about 250 astronomical units on a side of this image. And so in these simulations of the first stars in the universe, when we think about scale, we think about being able to simultaneously resolve length scales, time scales, density scales in many different ways. But let's talk about scale in another way. Let's talk about the way that we scale, the way how we inquire things of our data. And I'm going to return to this in just a moment, but if you imagine having one axis of the complexity of the things that we want to do, and then the availability of those techniques. Originally, not that long ago, but originally, as computational science was maturing as a discipline, the least complex items were very available. And as time goes on, more and more complex things became possible, but their availability was commensurately lower. And then as time goes on, we keep seeing this sort of progression where you've got some things that are not very complex that are highly available, things that are much more complex. And when I speak of complexity, I'm talking about the difficulty of dealing with all of the different sources of friction when dealing with technology. So, for instance, things as high level as booting an operating system or as low level as manipulating data. What we really want, and this is the ideal picture, is we want to have numerous things, very complex inquiries, processes, and so on that are highly available to people at all times. So this is going to be what I talk about a little bit more. And I want to propose an ansatz. And I've shown some evidence for this, but I want to propose an ansatz that as time goes on, software gets better, hardware gets cheaper, but the cost of people remains fixed. Yes. Fair point. So people cost the same. So I'll give an example. You can think about different types of software and how they shape your inquiry as being divided up into generic processes and specific processes. So if you look back at the Toomre and Toomre paper from the early 1970s, almost every single thing that happened during that calculation was written explicitly by Toomre and Toomre or their collaborators for that calculation. This includes all the way down to the level of the operating system booting up, loading. They wrote their own I/O processes. They wrote the integration techniques. They wrote every single step of that, all the way up to the point that they took a camera and pointed it at the monitor as it was going in order to record the visualizations, which incidentally is also how Honeymooners episodes were recorded in the 50s. I tried to find the video because a while back someone restored that visualization and put it online, but the last time I went looking for it, it's beautiful. The last time I went looking for it, the links had all died because it was part of someone's thesis project and they moved on from a university. But if that video is available, I highly recommend watching it. The visualizations of these first galaxy calculations that were done on a computer is just amazing. And as time goes on, pieces of software components move into the generic from the specific. So for instance, in the 1980s, we utilized commodity operating systems. Starting in the late 1980s, early 90s, we started to have message passing interfaces to enable parallel computation. We started to have I/O libraries that could abstract that away from us. We started to have higher order methods that could be utilized in software frameworks for computation, for analysis, for visualization, all these different things. And we started layering on thinner and thinner layers of domain specificity. And so the reason that I highlight this and I bring it up is because this is where the fact that software is getting better and hardware is getting cheaper and people cost the same means that we can divert more of our energies towards the things that we can't replicate with software, towards the process of inquiry, towards the process of thinking about our data and asking questions and doing things with it. And in fact, we can split this into the notion of the components of our computational workflow, of our workflows in general, that are focused on facilitation versus those components that are focused on inquiry. So in my abstract, I actually I mentioned that I was going to talk about a particular software package that I work on, and I am going to do that. And that's what the next little bit is about. But I'm going to return to this notion of how as scientists, how we interact with software and how we can design software to facilitate inquiry a little bit better. So if you're not interested in the thing that was in the abstract, go ahead and sort of tune out right now. But I'm going to talk about a piece of software that really is supposed to sit in between the person, and this is actually a person. This is not just a glyph and data. And the software is called YT, and it sits in between you. See, this is a little arrow indicating interaction between the two different things. And then even if that data is very large, See, it's very large in this case. I'm going to tell you a little bit about it. It's Python-based. It's community developed with a well-defined code of with a code of conduct, a governance structure. We've a little bit over 100 contributors. We deal with volumetric and non-spatial data. Now that this citation count is a little bit old, supports things like grids, particles, octrees, unstructured meshes. So, we use the same routines to analyze. People have used the same routines to analyze nuclear fusion experiments as they have to study the way that galaxies form. Arbitrary geometric representations, so like r theta phi as well as x, y, z. And the main focus of it, though, is to minimize the time to inquiry, to provide a common language that focuses on the physical rather than the data. I'm going to put up a list.
Very quickly, what code of conduct is?
Yes, absolutely. So a code of conduct describes the way that people that interact with the project and the way that people contribute to it can expect to interact with each other. So specifically, this is focused on providing structures for reporting as well as identifying inappropriate behaviors, which might be things like bullying, comments that are inappropriate, and so on. And we base this off of a code of conduct that was developed by the Python Software Foundation, which I believe also shares some with the Lovelace Initiative, or the ADA Initiative code of conduct. So this is actually, it's interesting that you bring that up because this is something that is becoming much more common in open source projects, particularly, and I'm going to talk about this a little bit later, particularly as it's seen that projects that occupy what can be thought of as volunteer time often self-select against people that are not like the people that are already in that project. And a code of conduct is a method of breaking down that barrier and trying to increase participation. We have a membership structure, so I'm going to put this up here. All of these people, have been nominated, voted on, and brought into the project as members. And so this actually has part of our governance structure. And the only reason that I bring this up is because I want to talk a little bit later about software structures and how that interfaces at this socio-technical scale, the point where people interact with the software. But getting down to the notion of what it does, imagine you have some simulation. I'm told that there are not a lot of simulators here, and so I should feel free to make unfounded assertions about simulations. Imagine you have some simulation, it's in a box, this is a conceptual representation, and that there's some region in that simulation that you're interested in. You can think about the different ways that we represent our data as breaking down into the lowest level, which are the bits that exist on disk. This is the set of ones and zeros that turn into values like 1.67 times 10 to the minus 24. That's what I mean by that. And these might be distributed across different files. They might be distributed across different infrastructures and so on. And then you have the data. And so this is the collection of information that according to some prescription, is a discretization of the model. So for instance, if you're dealing with a particle-based code, this might be a set of particles that have velocities, that have densities. If you're dealing with a grid code, it might have a grid of values. In essence, this is the medium level, and this is the part that most people deal with. This is where most people interact with their data. And then at the highest level, there are the objects. Right? This is the semantic information. This is where you look at a visualization of Stephanie's data or Andrew's data, and you say, oh, that is a dwarf galaxy right there. I'm looking at that object, and then that object has some information. I bring with me my understanding of that object, and that's where I interact with it. And so this is the level that for the most part we interact with data. And this is the level at which we really want to be able to interact with data. We want to be able to speak about physical concepts rather than the nuts and bolts and nitty-gritty of why I'm using big endian versus little endian, and why things are stored in JSON instead of HDF5, which actually does happen.
But in addition to objects, there's
Yes.
also the time domain, so you have processes.
Absolutely. So that's a very good point, and I think that's an improvement to this messaging that I should take into account, because you're absolutely right. Especially if you and I'm going to talk. I'll briefly mention Lagrangian coherent structures a little bit later, because I think that's an example of where the processes and the time domain become important in defining a conceptual representation of something.
Right, because then there are concepts above all that.
Exactly. Yeah, that's exactly right. And you're right. So as an example, you might have a grid-based code, and this is a grid-based code. You can see the grid here. And it might even be, you're solving for fluid flow over a domain, for instance, and so you're executing Riemann solvers or whatever. You might have adaptive mesh refinement in that system, right? So now all of a sudden, this is how we ran our first stars calculations. It was nested way down into there. All of a sudden now you're dealing with a situation where you have variable resolution in different areas. You might even have duplicate data that's bad. Now imagine that you're dealing with particle data, where you've got discrete points that might have affiliated parameters, velocities, for instance. But you're also, in your mind, you're representing this as a fixed system. And so you know that even though you've discretized your fluid, each point in the system still has an affiliated density, right? And so your representation of these objects internally, we look at this and we see, what looks like well, I'm going to tell you, it's a star-forming region. But the data is represented in a different way. It's represented as all these different patches of data that exist on disk that might be overlapping, that are different resolutions. And we can even look at it in a more abstract way. And we want to be able to interact with it on a very high level, looking at these objects and processes. But we have to deal with this. So returning to this notion of the layers of representation, again, we want to deal with the objects instead of the data. So we've got some simulation. And the simplest possible thing that we could do with this simulation would be to cut out some region, something that we're that we're interested in. And so we can apply a geometric selector. There are different ways of non-spatially selecting data. For instance, just select the ones that are above this density, below this density, that are topologically connected, that have that share this mean free path for electrons or something like that. We select that data, and that's what we're interested in. And so we've got this selected data, which might even be represented by a very large amount of data that exists on disk behind it. And they might be represented in many, many chunks of data that are heterogeneous, that are spread out over numerous files, that are spread out over numerous systems. But we still really only care about the fact that we've selected our sphere, and we are interested in what is going on in that sphere. And so we separate this into a couple different things. We separate it into high-level operations, where we abstract out the notion, if you've got a star that you're interested in, it shouldn't matter to you whether the data is chunked like this, whether it's chunked in small chunks, whether it's in multiple chunks that are spread out over many different disks, and we abstract that away. And so that's the idea behind these high-level operations, is to be able to operate on physical quantities. So as an example, one thing that you might be able to think about as you're thinking about simulations of galaxies is perhaps you have an isolated disk of a Milky Way-like galaxy, and you look at it at one instant and you see a giant molecular cloud. And then you look at it a little bit later, and there's what you think in your mind is the same giant molecular cloud, but this time, it's been distorted. Perhaps it's undergone some star formation. It's compressed in some way. It's moved around. It's migrated through the disk. And then you look at it at a third time, and it's changed shape again. How do you correlate those different molecular clouds and identify them as the same object? That's the type of physical reasoning and intuition that we want to try to make available through computational techniques. This is Lagrange coherent structures is one technique to do this in systems like that. And then there are the mid-level operations, where you're actually dealing with values of data. So for instance, you might have meters, inverse seconds, and then you want to get back out meters per second. So different ways of representing the data, applying metadata to it and carrying that along. And then now imagine that you're dealing with this, and you're actually dealing with co-moving meters in one particular discretization, and you're dealing with seconds, and you want to get back out proper meters per second squared. And so these are the types of mid-level operations that we also want to make available through this system. And I'm going to talk a little bit about pragmatic ontologies later on. And then finally, the low-level operations that are exposed through this system are actually dealing with pulling data off of disk. So imagine that you're a graduate student who's dealing with writing a new solver. Perhaps you have a new feedback prescription, and getting at the numbers exactly as they came out of the simulation is your highest priority. That should be accessible as well. So in this way, what I'm trying to describe here is this notion that regardless of where you want to enter into the process of inquiry, whether you want that to be in a very domain-specific way, talking about stars moving through a galaxy, SED generation, clump finding in star formation in star-forming regions, whether that's looking at providing your own methods for reducing and processing and visualizing data, or even if it's all the way down to inspecting the raw bits that are on disk, all of those things should be accessible. And that's where tools that focus on empowering individuals to really take control of their inquiry, I think can be very useful in fields like astronomy. So some other low-level operations like splitting a chunk up into spatial chunks in case you want to do spatial derivatives or something like that. Pulling from internal YT representations or cells, particles, elements, that sort of thing. And then finally, even things like synthetic observations. And I have this picture of generating synthetic observations because we had a workshop about a year ago where we worked on generating synthetic observations from CGM simulations, and then the next phase of this is going to be ingesting those directly into an archive, trying to make them look exactly like, or trying to make them in the same form that you would expect from COS, for instance. Nope, sorry, false alarm. So we ingest from a whole bunch of different types of codes. I won't bore you with that, but a whole bunch of them, including ones that discretize as octrees, those that discretize as patches of grids, those that discretize as particles, and then even those that now discretize as unstructured mesh. So based on the time, I'm not sure that I'm going to that it would be best for me to do an interactive demo, but I will briefly show one thing. And thank you to Gwen for letting me use her computer. So when I talk about all of this, I guess I can't anyway because of the parental controls.
You can do that.
No, it's okay. So I have a gallery of things as well, but one of the things we really want to do in lowering the barrier to entry is trying to ensure that it's very easy to access data, inquire of that data at whatever level you want. And this has been guided through interactions with individuals and students. So this is from one of my simulations. And I haven't talked very much yet about the process of visualization, because while this code, while YT specifically is mostly thought of it, by people as visualization code, the visualization is really an afterthought. Not an afterthought, but it's really built out of the necessary tools that go into the process of analyzing the data. And so I want to highlight that here. This is a volume rendering of a star-forming region in the early universe. And if we look up here, this is a phase plot. So this is a distribution as a function of density and temperat of the cell mass in the simulation. And so we look at this, and you can say, okay, great. So now I see a distribution here. But we can actually highlight specific regions and then look at which isocontours correspond to this. Now, it's really easy for me to click this slide back and forth, and you think that, oh, I'm doing this manually. But no, I had to write a little bit of code to do that. So we can actually drive our inquiry through the visualization process. And so these are cool images. This was set as the background of my Gmail for a while because I thought it was really pretty. But the same underlying machinery that does this is also the same underlying machinery that computes synthetic observations, that does ray tracing through domains and accumulates column densities and so on. And it's also the same machinery that we use for identifying topologically connected sets. And it's really a natural growth out of that we're able to create visualizations. This is a video, but I only have a still frame here, of a star-forming region that blows a bunch of material out. And the reason that I'm putting this up here is because Stella Offner sent me this, and she included a note in the email that said, oh, and by the way, this was made by a 10th grader. And I thought that was really cool because it's this method of trying to break down the walls where you can have things that are accessible to people at many different stages in their career, particularly the stages of the career. If you think about when you were a graduate student or maybe an early postdoc, you're moving between research groups, you're changing maybe the simulation of the data formats that you get. And it's a great impediment to have to relearn all of the different necessary mechanisms. So if you have one tool one or multiple tools that can read from the same types of data and conduct the same physically motivated analysis, then that reduces the overall barrier to entry for people at just about any stage in their career.
What does it mean that 10th grader made that? I could say my cat.
Mhm. But your cat didn't make it. No.
My cat
So
could've just-
a 10th grader was working with Stella and was able to, on their own, download, install, and utilize the code to analyze a data set that Stella gave them.
Wow. Okay.
I thought it was cool.
Yeah, but did she understand anything about what she was doing?
I can't answer that question.
Like, what's the nature of the data set? I guess that would help us.
It's a star formation simulation with radiative feedback.
It's straightforward to use, but you have to make some choices to actually use
Mhm.
YT in such a way that hopefully you have to understand something. Like she can't, it's not just like a GUI with a slider to make it look pretty. You make actual choices as to what densities you want to highlight and stuff like that.
So my assumption is that based on conversations, they came up with a particular way to visualize it, and they designed the visualization together. This is, a star. And then, it gets used for, and I like this image particularly because, and I was being very flip there by going through it, but the notion here is that the same underlying machinery gets used in many different domains. This is a stellar interior. I can't remember the specifics of the simulation, but this is actually a simulation of convection in a hydrogen-helium layer on a neutron star. And so, all of these different domains can utilize the same system, the same mechanisms of addressing the data, talking about densities in the same way, temperatures in the same way, and then you can utilize the same scripts regardless of the type of data set that you're analyzing. So I want to show this one particularly because I think this is a really interesting application. Elizabeth Tasker, who's a professor at University of Hokkaido, used YT to identify regions, connected regions with negative escape velocities from the plane of her disk. And to use this to identify GMCs and to say something about the way that they migrated through her disk. And you can do this because it abstracts out but makes accessible the lower level data representations. And we can do things like simulated magnetic field observations in collapsing cores and so on. And then also halo analysis. I'm going to keep skipping. This was generated by Hilary Egan, who at the time was an undergrad. She used the same machinery that we used for volume rendering to generate a synthetic spectrum module. And the coolest thing about this, I don't have the actual noisy one here, but she also added on a way to make these beautiful spectra ugly by adding in noise. And then very simple things like distributions. Observational, synthetic observations with X-ray clusters where you can take a simulation, describe the way that you look at it, and then say what would it look like through NuStar, what would it look like through Astro H, what would it look like through XMM Newton, and so on and so forth. Oh, and I want to show a movie. So this is a movie, and I know I just was bemoaning the fact that YT gets thought of as a visualization tool, but this was a movie where using, again, the same things that generate the quantitative plots that go into published literature, we can generate a movie that, oops. So this is actually, let's see if it'll play. Oh, not burgers. Yes, please. So we can use we use the same underlying machinery to represent the data as we do to analyze it and produce quantitative plots. Yeah. It might just need to be reloaded, so I'll try that.
I will try one more time.
Okay, and then I'll give up on it. It's a pretty movie. And from the still frame, you can see, yeah, we can just, I'll play it another way somehow, someday. Oh, there it goes. So a couple things I want to highlight. These are isocontours. We're going to zoom out from one of the regions that the first star formed in. But I chose these isocontours based on the chemical properties at those densities. So based on the fact that this is where three-body formation takes over. This is the loitering phase. These are the different relevant physical properties that are going on in this system. We choose where we put these visualizations, and we can use the same machinery to generate, cool movies. Now this next segment is from a different simulation of one of those stars igniting, exploding, and then enriching its surroundings. And I want to bring your attention to the colors. The colors here are from a black body spectrum. We applied some approximations for scattering and absorption, so they're not realistic. They're not realistic, but they are realistic. There was air quotes there. And then we convolved them through Hubble filters, or not, we applied Hubble filters to them in order to generate an RGB image. And so the idea here is that we're using, we're driving the visualizations based on our scientific and semantic understanding of what it is that we're looking at. Oops, how do I get to the next slide? I can do it. There we go. Okay. There we go. Present. Okay. And thank you again, Gwen. So the principles for how we decide that we're going to engage in something, we've written these out and we've discussed them. What we want to do is we want to identify the minimum necessary complexity for the maximum possible utility. So that means we have to say no to a lot of different possibilities and projects. We want to ensure broad dissemination and utilization of the technologies that we develop. It's no use to anyone if we use our $10 per line of code to write a bunch of stuff that's not going to get used, that doesn't have high scientific impact, that doesn't do things that are useful for people. And we want to ensure that it's sustainable as an endeavor. And I'm going to talk for a minute about sustainability before the end. But I want to show off a couple recent projects. Like we're doing higher order finite element method. And here's an example of first order finite element and higher order finite element. Ooh. You can see it slightly curves here. We're working on mechanisms for providing and exploring published data. So you can actually go to these first two, download full copies of the data. If you go to demo.use.yt, you can actually utilize an interactive Jupyter notebook to explore data from Nathan Goldbaum's papers about his isolated galaxy disks. And here's the link for that. He's got a, there's a galaxy visualization widget that Nathan designed so that you can interactively look at these different things, but you can also explore the data and drive your own inquiry, as long as it doesn't get too compute heavy. We're working on things like compressed bitmap indices to speed up computation, or to speed up data selection processes. So imagine that you've got a whole bunch of particles. These particles might be galaxies in a catalog. They might be dark matter particles. They're distributed in some unknown way across many different files. What you really want is a very quick way to select out particular areas of those without overreading data, without keeping too much of an index in memory, and then to generate a spatial tree from that. So Megan Lang, who's a postdoc at NCSA, has been working on a project to implement compressed bitmap indices. So using a technology called enhanced word-aligned hybrid compression technology, you can actually store a huge amount of ones and zeros in a very, very small array. And so what we do is you can build up an index, identify the regions where you might have collisions in that index, and then only refine in those regions and store to disk. You can without assuming anything about the sorted nature of these things, you can conduct extremely fast queries for neighbors and so on. Semantically meaningful data, which I mentioned earlier, threading through meaningful units that are flexible and that can can provide information about your data. So for instance, meters, seconds, meters per second. But also now imagine going in the opposite direction, starting with an ontology of things that mean, for instance, magnetic field energy, and what are the necessary fields in order to back that out? What do you need in your simulation in order to get this type of information? And then finally, the data deliberator. See, there's all these words on this slide. The data deliberator is the method, is something that we're exploring to provide access to data to anyone. So it's designed to be a system that can be rolled out at any institution, or that there might be fiducial representations of that at many different places. And then people can guide their own analysis of data. And so we're working with a couple different partners on this, including at San Diego, TAC, at Texas, at NCSA, and a couple other places as well. So let's see if this video plays. This is an example. So Kasper Kowalik is a postdoc at NCSA who just sent me this. This is an example. Oh. That ad website. Okay, here, I'm going to hit OK. Let's see if it, well, I'm sorry, Kasper. I'm going to go to the next slide. Essentially, the idea behind it, though, is to provide mechanisms for accessing published data, inquiring of that data, and then, most crucially, publishing the results of that inquiry. And we're working with, as I mentioned, a couple different partners, but we're also engaging with publishers on this. So we're also doing immersive scientific visualization. This is me. I've got a thing on my head, and I've got two wands in my hands. And I've long been an extreme skeptic of high-end visualization, especially virtual reality, ever since it cost $15 for like 3.5 minutes of Dactyl Nightmare in 1994, where the pterodactyl comes down and pulls you up and whatnot. And I'm actually an extreme skeptic of things like this until I saw that the same software you use to do these high-end, Oculus Rift, Vive technologies can also be done on a mobile phone. You don't have to rewrite your software. And you can also do things like put Minecraft into those. So this is cute, right? Oh yeah, you're doing Minecraft in the Oculus Rift, so you're doing whatever. That's cute. But the thing that maybe isn't immediately obvious is that the data that's being presented in Minecraft is actually a galaxy simulation. And so one of the things that we're working on in our group to really try to do is to engage with people where they already are. For the cases of graduate students and postdocs, what we're trying to do is we're trying to make the inquiry that they're dealing with easier. And when it comes to things like education and public outreach, you need to go where the people are. And it turns out that people are in Minecraft. And so if you can bring to them things like galaxy simulations and teach them, show them the power of computing and the power of how we can inquire of these data sets in new ways, then potentially you can help to build greater relationships there.
Somebody already made StarCraft.
Did they? Oh yeah, that's true. Yeah, that's a thing. So this YouTube video, which I won't even try to show, is designed just to show that, as I talked about the different layers of representation, if we engage at the right layer, you don't have to rewrite your software to make it accessible through something like high-end virtual reality, as well as something like a mobile phone, as well as something like something that sits on your desktop. So this is a video that just shows loading up actual scientific data sets into one of these systems, into a holodeck, basically. There we go. And then things like non-Cartesian ray tracing. And so the previous one was done by Robert Thompson. This is by David Hanash. And I'm just about at the end, so I'm going to skip through this. But I want to just thank some of the funding agencies that have supported a lot of this work, like NCSA, the Gordon and Betty Moore Foundation, and the NSF, and then a bunch of the group members in my group. And I'm going to end by talking about where I think that we can go with this methodology of thinking about how people engage with software, and particularly how that engages with the scientific process. I think that we can take computational techniques, we can take science in a broader, a deeper, and a further direction, broader being to multiple different types of scientific inquiry, so different domains of study, deeper in asking deeper questions, and then further in making it more accessible to many different people. And I want to end by talking about scale one more time, and really talking about sustainability. And so I've been to a bunch of sustaining scientific software workshops in the last couple of years. the notion that people that build tools aren't being rewarded in their careers is very prevalent. And this is something that instrumentalists dealt with and are still dealing with, but that people that develop software in computational science are also now dealing with. And the question that's always implicit at these is always, what are we sustaining? When we talk about sustainable software, when we talk about sustainable science, what are we sustaining? And the first thing that people always say is, well, obviously we're sustaining the software, right? But I don't think that's really true. Ideally, we're sustaining our ability to conduct scientific inquiry. And really, even more specifically, we're conducting inquiry via software. So we need to be able to sustain that process. If you're dealing with data if you're dealing with data, you need to assume that your methods of interacting with it, whether that's through something like CFITS.io, whether that's through something like HDF5, whether it's through something like a CSV reader, that effort needs to be sustained. If all of a sudden these pieces of software stopped working on whatever computer you bought next year, that would be a problem. That would not be sustainable. And the question then becomes, are we talking about sustaining specific software? And if we start down that road and we start to think, are we actually sustaining people, careers, the future? Is that what we're talking about? Because I think it is, for the most part. And so there are a couple different definitions, things like keeping up with bug reports, adding new features, working on new hardware architectures, enabling people to learn how to use it, growing new features, producing the same results. Is software sustainable if it doesn't produce the same results now that it did 10 years ago? Is that something that we need to prioritize above things like bug reports? And then transitions between people. In particular, I know that at IPAC, Bruce Berryman's talked a lot about the transition of Montage from being his project to being a project that gets utilized in a broad, or that gets developed in a broader community, for instance. Things keeping to get funded. And then finally, the scaling relationship. This is my favorite equation because this is Amdahl's law. It says that you are limited in any parallel process by your non-parallel component. So imagine if 10% of your system is parallelizable, is not parallelizable, that will then become the rate determining step if you infinitely scale out. And that's the problem with human endeavors, is that people can be bottlenecks. They suffer from things like, software and people suffer from bit rot, from burnout, from not being interested in things anymore. And then there are a couple of mechanisms and impact for this. Designing software so that it's technically easy versus technically challenging, and socially challenging versus socially easy. Instituting social change is a really hard thing, particularly when it's how people interact with their careers and how they interact with their funding streams and how they interact with other people and their students. But doing things that are technically easy versus technically challenging can be much more straightforward. And we can actually think about these axes as functional versus problematic and detrimental versus humanitarian. And then also things like product versus project when we talk about software. Are we talking about this software as a product, as something that you want people to go and download and use and then tell you how great you are? Because that sounds great. But is it also something that people will get an investment in, that will participate in, and that they can then use it to further their own career? Is it a platform or is it a stool? A product which has one-way distribution, a project which has multiple ways, or a product where you're thinking about the thing, and the project where you're thinking about the people. I will continue to skip through because I am seeing the time, but I do want to end with one quick comment about unpaid labor. When scientific software in particular often suffers from this notion of unpaid labor, there's this, I think I'm using it correctly when I say there's this tragedy of the commons, right? People, nobody wants to fund the whole thing. And so people contribute little bits of their time. And this is great in one sense, but in another sense, it self-selects against those who may not have the time to contribute. And so if we focus too much on giving credit to everybody that volunteers their time, in their after hours, that sacrifices their career, then we're necessarily self-selecting against the people that don't have that opportunity. And that's something that Ash Dryden has actually written about in the context of open source non-scientific software, or maybe scientific, but open source software more broadly. And so 2 takeaways. Actually here, I'll keep skipping through, blah, blah, blah. I want to end by saying this is bigger than astronomy. Scientific software, all these different endeavors through which people collaborate, communicate, do things, contribute to things. This is a bigger process than astronomy, and there are groups that are looking at this and studying it quantitatively as well as qualitatively. And I'll end by talking about scale in terms of scaling of, well, I won't tell you what we're scaling yet. But if you think about a network, and you think about multiple connection points in that network, if you've got one person in the network, they can't talk to anybody. If you've got two people in the network, they can talk to each other. And if you've got three people in the network, they can all talk to each other. And so the value of a network doesn't scale with the number of nodes in that network. The value of a network scales like the number of nodes squared, because it scales with the connections between different things. This was true, the term Metcalfe's law. Metcalfe coined this, I think, in the earlier days of the internet. The notion that, the internet is great, but if there's only one website, if there's only one person on it, then all they can do is talk to themselves. But it's great because it scales like n squared. And we can think about this, if you think about this from the perspective of people, if we build communities around projects, then we scale those projects as the number of people squared rather than the number of people. Because if we facilitate inquiry, if we facilitate direct technology transfer, if we lower the barriers to people being able to collaborate, we can all be more productive.
What about latency and overload?
Yeah, those are also both problems. Overload especially.
Okay.
Those are problems. So let me preface this by saying I'm presenting an idealized picture here. You can tell by the cartoon drawings.
They're all happy.
Yeah, they're all happy people. Yeah, see, they're all smiling. I had a slide earlier where I curved it down. We see this now, with data, with interconnection of data. If you think about, in particularly, you think about the recent LIGO discovery and the quick follow-ups that were done on that. We already implicitly know that we can scale the value of a network of data that can be queried, right? But scaling that with people is something that I think we know that, but we need to directly engage and architect. So that was the end of my talk, and I want to say thank you very much for having me here. It's been an amazing time, and I'm really grateful for the opportunity to talk to and meet so many of you. So thank you.
Questions from that?
What does YT stand for, and how much is all this linked to some basic format? I mean, Astronomy Web have the FITS format, which has
Yes.
done wonders for exchanging
It has.
different wavelength regions. So if somebody comes with a pretty wild coordinate system, cylindrical would be only very mild, but much worse, can the software work, or do you first separately have to get onto a standard system with which the software works?
So to answer your first question first, it stands for yours truly, which it comes from a book. The second question is very interesting to me because right now we mostly deal with metric data spaces. So data spaces where you follow the rules of metric geometry, where you've got a dot product, you can move it around and so on. We are moving into non-spatial coordinate systems. We can already handle coordinate systems where in your Jacobian you have no off-diagonal elements. So for instance, if you traverse in one way, so as an example, I used this example to Andrew earlier, having pressure coordinates rather than altitude, for instance, in an atmospheric simulation. We can deal with that. Dealing with systems such as fully relativistic systems is on our near-term roadmap. So dealing with numerical relativity simulations, which from what I can tell so far is going to require the necessary developments to enable the crazy coordinate systems that you just described.
Thank you.
So you talked a lot about sort of topics that I would generalize under the idea of sort of inclusivity.
Mm-hmm.
So being able to have a larger group of scientists ask interesting questions of data. So I'm interested in if the YT project is also focused on how to make YT inclusive in that way.
We are, so let me preface this by saying that the group of developers and users is more homogeneous than would be ideal. It is not as diverse a group, but we are extremely interested in increasing the inclusivity. And so what that usually means, that means oftentimes, and I struggle with this, because it means talking about things that are uncomfortable and talking about, in what ways are we not inclusive? What are the different ways that perhaps there are implicit biases in the way that we address a group, the way that we expect responses, the way that we might socialize? Is there a cliquishness? Is that, all these different things are barriers to inclusivity that are difficult to talk about and that are really important to talk about. So I think we are focused, but I don't think that we have a lot of work to do in that. A lot, yeah.
A much higher level version of that. How many folks are the kind of people that work with observational data as opposed to simulation data?
Right now, not as many as we would like. Probably a couple. It's actually really low. Most of our inroads to that have been through PPV cubes. So like a couple years ago, Eric Roslowski and some folks used YT to make a nature cover with a data cube from ALMA. But for the most part, the people are simulation folks that maybe use observations. One of the things that I didn't talk about is there are actually a couple projects working to bridge that gap. There's one that's headed out of Caltech just down the way called Trident, which is all about generating synthetic observations of the CGM. And then there's the photon simulator, which I did show, which generates synthetic X-ray observations. And those people really try to bridge the gap. Like the lead developer of the photon simulator now is full-time an employee at Chandra, for instance. And so he's very much bridging that gap. But yes, sadly, our diversity in terms of observation versus simulation is not what it could be.
How do you see interacting with databases where they have their own structures and they're not maybe as responsive as you need them to be?
Yeah, so that's a great question. We actually, I would say that we have these different levels of interacting with things, right? The main philosophy that we go by is that there's the front end, which deals with the data as it exists on disk. So we've written different front ends that can actually query from SQL databases for catalogs, and that can query over HTTP. And then once that information has been, once we have an I/O method, a method of regularizing to the field names, so like normalizing the field names and getting a little bit of metadata and index data, then we can deal with that the same way that we would other data sets. But for the most part, that's mostly useful with Halo catalogs, for instance. So Halo catalog, dark matter Halo catalogs. I wouldn't pretend that it would be of substantial interest for things like survey catalogs. It might be, but I don't know.
I'm thinking more of relational databases.
Mm-hmm.
Where
Yeah, exactly.
Really.
Yes. So the front ends themselves deal with a lot of the data selection. And so we can push a lot of data selection into the relational database. Because the nice thing about relational databases is you can decompose the query and then farm it out into the different to different compute nodes or something like that. So because it can conduct a dependency analysis of the query that you're sticking into it. So we can push that all to the relational database because they know how to do that really well.
So following up on the question of sort of observational analysis within YT, what do you see more long-term? What do you see as the role of YT in that? I mean, I can see sort of extending capabilities of looking at just theoretical sort of simulated data sets, but it's, as everyone knows, one of the keys is being able to analyze the simulation in the same way that we look at the observation.
Yes.
Do you see YT as a proper meeting ground for that? Do you see it as a stepping stone towards more complex things like what LSST is doing, of building their, very complex? Where do you see this all fitting together in the next 10 years?
What I see YT as being is the framework out of which an application that can generate synthetic observations can be built.
That's your goal. Okay.
Yeah, I see it as being and I'm sorry that this is getting recorded because this is going to sound very egomaniacal, but I see it as more fitting the NumPy for spatial data or NumPy for volumetric data, rather than sort of the high level processes. It's designed to be a mechanism that really sits next to the data, applies minimum semantics, and then people build their analysis pipelines. And so that's why things like Photon Simulator and Trident, I think, fill that role. They're building out of it.
Mhm.
Any more questions from that? All right, let's thank him for a great talk. We'll be going to dinner. Let me know if you're interested in joining us. We'll meet in the lobby at 5:45.